actually a winter in Israel, so I don't know with you or we just not had time to move very nicely. But Europeans are used to it anyway, we're not. So just a few quick announcements and a general idea of what we want to do here, and then we'll get started. So firstly, thanks for support. The school was made possible by the generous support of the European Union, the ERC, the European Research Council. IBM gave us a very nice amount of money also to cover travel grants and other costs. And the Bar-Ilan University, specifically the Department of Computer Science, the Faculty of Exact Sciences, and also the Research Authority have all supported this event. Other thank yous for the local arrangements, Yoni Konberger, who's outside welcoming you, and she has done most of the work here, so a big thanks to her. And also to our guest speakers who will be speaking on Tuesday, our guest lecturers I should say, Yuval Shai and Shai Halevi from Stephanie Ireland and IBM. So who's here? We have quite a diverse audience actually. Internationally we have 32 people from a number of different countries. Denmark and Germany are coming out on top, but we have nice representations from quite a few countries. So that's the map. Clearly, Europe is the strongest here. From Israel, we have about 40 participants from all of the universities. So we welcome you also all here. Although a number of the Israelis are not yet here because they're all stuck in traffic. That's the way. When you come from close, then it takes you much longer. When you're coming from Europe, then you know how to get here on time. So what are our aims in this school? The basic premise is that we view secure computation in general, and I guess all of you here will otherwise wouldn't come, as a central subfield of theoretical and applied cryptography. It's a highly active area of research. It has been for the last 30 years, but it has ups and downs. And when we talk about efficiency, which is half of the title of this winter school, if you look in the last 4 or 5 years, it's thriving again. It has become there are a considerable number of papers published in all of the top tier conferences about this topic. The theory, it has been strong for the last 30 years, and although sometimes you might think that, well, we know the answer to everything, it's surprising how many more important and fundamental research questions are out there. But I won't give you mine, you have to come up with your own. There's also growing interest in efficient solutions from governments and industry, and this is brand new. I think 5 years ago, or 6 years ago, cryptographers from academia were always trying to push what application can we find. It was like voting, and we're trying to find where can we apply it in privacy-preserving data mining, but it wasn't really clear there was much interest. Today there is a lot of interest. I'll give you an example soon of a real example of. I actually have 2 examples from the last month of people who approached me looking for solutions to a specific problem that uses to try and solve it using secure computation. So we're at a sort of a stage that if we can supply good solutions to people outside of the cryptographic community who are interested in them, then we can take this field, which has again been around for 30 years but hasn't managed to cross into practice. We'll actually be able to do that. So that's another aim of trying to boost research in this field, is to be able to do that. Unfortunately, though, it's not an easy field to get into. Reading about secure computation from books, which are few and far between, from the papers is very difficult. There are different notations, different terminologies, very diverse amount of material out there. Sometimes getting a few days where you can study it in depth and get your foot in makes it much easier afterwards to go to literature. So again, that's very much one of our aims, to help the entrance to the field, and people who are already in the field, then again to get a good coverage, or broad coverage on the different topics, which we'll talk about in a minute. So what are the 3 topics? One is a topic for each day. Today we're going to be talking about the foundations of secure computation. So we'll cover definitions is the first session. Afterwards, fundamental feasibility results. We have Yale's results for two-party computation, GMW, which is for malicious party and the multi-party case in the afternoon, the first session in the afternoon, and BGW, which is information theoretic computation, in the last session of today. So today, the fundamental basic results, again, these results are indeed 30 years old. Definitions, you could say, you could argue more like 10 to 12 years old, depending how you count. Tomorrow, we're going to be talking about techniques for efficient, secure computation. And we'll study Sigma protocols and oblivious transfer, which are the most popular tools or most popular and useful basic building blocks that are out there. And in the afternoon, we'll talk about more high-level protocols for general secure computation in the two-party setting that's efficient, and also some specific problems like securely finding the k-rank element of the median and set intersections. So there we'll look at how we can actually take the general techniques, the general ideas that we've studied, and actually apply them to get actual solutions. And on the last day, we're going to study brand new results that are very, very recent and very exciting. First, there's the fully homomorphic encryption, which everybody's heard about over and over and over again. But having 3 hours straight on it, I think will really help us to understand how it's done, what its limitations are, and what's next. And we also will also be studying new results on efficient, secure computation that with results that sort of merge the honest majority and dishonest majority settings. So first we'll look at, Yuval will talk about secure computation with an honest majority, doing that efficiently, and then something called the IPS compiler, which shows how you can actually use information theoretic results and the setting of honest majority in order to solve the setting of dishonest majority. And you mentioned that Shai and Levi will be giving the sessions on fully homomorphic encryption. Of course, this is far from everything. The amount of material out there is overwhelmingly enormous, so we're trying to cover a few very important topics. There are some very, very important topics which we're also not going to cover. One is adaptive security. We'll only be talking, or maybe Yuval will talk about adaptive security, but everything else, and Benny a little bit, will be static security, static corruption, which I'll discuss with you in a minute. Security under composition, we're not going to be talking about. And other models and definitions that there are many different models, many different definitions that are important and worthwhile looking at. We're only going to be dealing with the very basic ones. Again, our hope and belief is that once you have the material from this school under your belt, then it's much, much easier to go out and extend to the more advanced material as well. Just a couple of announcements regarding the school. Lunch is going to be downstairs in this building, which is lucky because it's raining. Please bring your badge because there's an exact number of seats, so it's only open for registered participants. Tomorrow night we're going to Jerusalem, that's a social event. We'll be going, the bus will leave from here and we'll return to the hotel and to the university. We'll be going to the tunnels which go underneath the Western Wall, so we'll be seeing things from 2,500 years ago. And then we'll be going out to dinner in Jerusalem. There's a change of schedule on Tuesday morning in order to let you all sleep a little bit more after getting back from Jerusalem. We'll be starting at 9:30 and not at 9. And that changes also the bus times from the hotel, but everyone at the hotel has received information about that. And for wireless connection, there's a public network called Bar-Ilan Guest. You don't need any password. Just a word of warning from groundbreaking research I read in the Communications of the ACM. It says that they studied for a long time and they realized that using laptops in class might be a distraction for students. Very surprising result, but the one to be worthwhile thinking of. Okay, let's get started. Just one more comment. It's where it's quite a large number of people, actually more than we expected, so we're very happy for that. But we still want it to be a school-type atmosphere. It's not a conference where everyone, please feel free to ask questions, stop me. Ask for clarifications, ask for more details about anything that you're interested in. We'd be very happy to be interactive. Okay, let's get started. So, by the way, I'm Lindell, in case you don't know. This is Benny Pinkas over here. So, we both welcome you all. Okay, background and definitions. So here's a request I got from 1 month ago, and then I'll tell you a request I got about 2 weeks ago. Some non-profit organization in New York, which the details are sort of kept vague on purpose, is under contract from the US government, and they're doing research on criminal justice, And this organization asked the US immigration authorities for the list of something called alien registration numbers, which is sort of like ID numbers of immigrants. So they wanted these alien registration numbers of aliens that were arrested in New York City, and they wanted to see which of them are on their list of aliens. I don't know why they call immigrants aliens, but there you go. But neither party could hand over their list for privacy concerns. The government organization was supposed to give the information, or sorry, the US immigration authorities were supposed to give out this information and said, we can't, it's private, maybe yes, maybe no, but they can't. And the other organization didn't really want to give away what they were doing to the immigration authorities, because maybe they had also people that weren't so legal anymore, and they didn't want to give out that information. And this is exactly secure set intersection. What the two sides simply wanted to do was to find out who was on both of their lists. And they were actually looking for a way to do this and to solve their legal problem. This was actually a problem between lawyers, but there was a computer scientist who was a friend of one of the lawyers and said, actually, there are solutions out there. So this is exactly secure set intersection. Unfortunately, there isn't a commercial piece of software up and running that they could use, but we're working to solve that in the next couple of years. But this is just to show that it's actual real interest. Another, about 2 weeks ago, I was approached by an astronomer, actually, in the States, who said that there are a number of different labs, and they are all spotting stars, looking at stars, looking for planets that go in front of stars, and it's very, very hard to find them. There are about 1 million stars, and about 1,000 have planets going in front, orbiting in front of them, and it's very hard to find them. The problem is there are a lot of false positives. There are about 10,000 ones which look like it's a planet going in front, but after months' work, you realize that it's not. Now, what you want to do when you see something which is a potential, you'd like to ask the other labs if they have already ruled it out. You don't want to tell them that you're looking there, because if they haven't ruled it out and they haven't seen it, then they're going to scoop you. They also don't want to tell you too much about what they're doing, because then you'll know where they're looking. And what they do now is they use a trusted party. They actually go, they find some scientist that they all trust, and they give them the list, and then they ask if he can find out from that other lab, and that works very nicely for them. But this person was looking for a better solution. Again, classic secure set intersection, and this is what I mean when I say that there is real interest now coming out of a number of different areas, people looking for solutions to these problems. Okay, so what is secure computation in its generality? We have a set of parties with private inputs. Actually, it doesn't have to be private inputs. Secure computation can sometimes be interesting even without private inputs. And what the parties wish to do is jointly compute a function of their inputs while preserving certain security properties, which I'll talk about in the next slide. The important thing is, all this depends exactly on the model you define, but in general you want the properties to be guaranteed even if some subset of the parties are corrupted. By corrupted, they can behave in different ways, which we'll talk about soon. But for now, we'll just say they maliciously try to attack the protocol and somehow get information they weren't supposed to, or do something else that's bad. And importantly, this very, very general definition can essentially capture any cryptographic task. That's why when we talk about the theory of secure computation, we look at it as such a fundamental notion, because basically it solves essentially anything we want to do cryptographically, and therefore if we have general feasibility results or infeasibility results, these things carry over and tell us about everything else we're trying to do in crypto. What are the security requirements that we want from a secure computational protocol? So let's play a game and think about what we want from a secure auction with secret bids. So anyone want to throw out a property that you want? What would you want from a secure auction that has secret bids? No one's supposed to learn anything but the winning bid. So what's the first thing? Let's see, we're not into the interaction too much. So let's talk about privacy. The adversary may want to learn the bids of the other party so that it knows how they behave in the auction, in the next auction, to use that information to do something they weren't supposed to do. But what else can go wrong in a protocol, or in an auction protocol? Correctness. You want to make sure that the party with the highest bid will win the auction, and not some other, not an adversary who actually gives the lowest bid and makes it look as if it was the highest bid. That's correctness. But what else would we want from an option protocol? Is privacy correctness enough?
Verifiability.
Okay, so verifiability is sort of outside the realm of, I don't know, maybe it's not outside the realm, but verifiability means that way of everybody checking that it was actually correct. Or do you want a paper trail?
No,
if you want a paper trail, it's out of the realm. If it's verifiability, then just the fact that it's a secure protocol gives you that. You're absolutely, well, there's a problem that people may not believe that the secure protocol is doing what it's supposed to do. But if the secure protocol guarantees correctness mathematically, then verifiability is sort of automatic, I would say. The problem is with elections, for example, it's not enough, and that's where you want a paper trail. You want to be able to convince people who aren't cryptographers that it's actually working, and their verifiability is a huge issue that sort of goes beyond what we can do in computation. So there it's. But something else the adversary may want to do is just simply be able to give a bid which is $1 higher than the other highest bid. So the adversary doesn't even know what the highest bid was, but somehow manages to mold the messages to play around with the messages to give a bid which is higher, always guaranteed to be higher by not too much. And that's a problem that we call independence of inputs. The adversary was able to make its input depend on the other party's inputs. And we definitely want to prevent that as well. What about an adversary that would like to make the auction fail if it didn't give the highest bid? So it somehow learns the output first, and then realize, wow, that I didn't give the highest bid, so I'm going to make the whole thing fail, and the next time I'll give a higher bid. And in this way, give a higher and higher bid until it actually succeeds in winning the auction without giving a much too high bid. So that's also something. This is something called fairness. Why fairness? What we're basically saying is that if one party gets output, then all the parties should get output. It shouldn't be possible for an adversary to get output without everybody else getting it, because then maybe it could make the execution avoid. So that's this list that we just said now. Privacy, only the output is revealed. Correctness, the correct function is computed. Independence of inputs, you can't make your input depend on somebody else's. Fairness, if one party gets output, all do. And guaranteed output delivery, which is very close to fairness, but it's not exactly the same. It means that an adversary can't prevent the protocol from concluding successfully. So how would we define security given this list of properties? One option, and the old option, which I guess would go back to the 80s, but appears all throughout, and there's actually a good reason why sometimes you'll still do this, but in general, the first option is to analyze the security concerns for each specific problem. I have an auction, I sit down and work out what the properties are, and I give it a general ad hoc definition specifically for an auction. Afterwards, I do the same thing for elections. The problem is that this is dangerous. Because, for example, in elections, how do we know that all the concerns are covered? In elections, I might think that privacy, correctness, and fairness are enough. Independence of inputs. Would that be important in an election? Yes or no? Right, does it make sense that I could make my vote the same as somebody else's vote? Why would I want to do that? So maybe I don't care about it.
But if there's multiple arrangements, like multiple members of parliament, for example, you might want, depending on the voting system, you might want to give more to this.
Exactly. So it actually is a real concern, because I might want to say, okay, there are a number of parties, but not all the parties will actually even be represented in the parliament at the end. So I'd like to give my vote to this party, but if they don't get enough votes, then I'll give it to someone else. I'd like this representative to get in, but if they're already in, then I'll give it to my second choice. And that sort of thing, if it was done en masse, would actually very much bias the election. So it's not easy to come up with the exact requirements for every task, and therefore this is a problematic approach. Also, it means hard work for every application that you want to come up with. You can start defining from scratch, think about all the properties from scratch, and define everything properly. The second option is to come up with a general definition that essentially captures all or most secure computation tasks, and then derive specific definitions for specific tasks directly in a very, very easy way from the general definition. And the properties of any such definition will be, you'd have to have a very well-defined adversary model that would be relevant to many tasks, a well-defined execution setting, what do the real parties do, how does the protocol run in the real world, and you want the security guarantees to be clear and very simple to understand. because that's very much the goal also, I guess, of the verifiability. If I want somebody to could be convinced that this is actually doing what it's supposed to do, then it's important for them to understand what is being computed, what the guarantees are. So that's the approach we're going to take. And it's been a very, very successful approach. It's proved a successful approach. And I'm going now to build up with a number of different parameters that we need to define for that, and then I'll get to the actual definition. So the first thing we need to decide is, what's the adversarial behavior? What can an adversary do? And there are a number of different models. I'm going to give mainly focus on two of the most classic, and then mention a recent one which can be helpful. The first model is a very benign sort of model. The adversaries are what we call semi-honest. They run the protocol exactly as they're supposed to. You give them code for a protocol and actually run that and nothing else. But all they try to do is look at the transcript of what happened during the protocol execution, and based on that transcript, they try to learn more information. So if I sent a value to the other side, I can't rely on the fact that because it was only computed upon and actually given it, for example, by the user interface to that party, they won't see it. On the contrary, everything that was sent is actually seen. It's a very benign type of adversary, but it can actually have, it can actually be very useful in a number of scenarios. One could be where the parties actually trust each other, but by law, they're not allowed to give information out, and then maybe this would be enough. I'm not a lawyer, so I don't know. But one setting where it definitely would be enough is if you want to model inadvertent leakage of information. So let's say two hospitals want to run some secure computation on their data, but what happens is they're worried I'm worried if the other hospital's database gets broken into, or computing gets broken into, then essentially my information will also be stolen, because the protocol that we run, the joint computation that we use, may be leaked information to them. But if you're using a semi-honest protocol, then you know that there are no remnants whatsoever, because whatever we ran, nothing is learned except for the output. The inadvertent leakage information is definitely modeled very well by semi-honest adversaries. A malicious adversary is your super adversary who can basically do anything that they want. It's an arbitrary strategy. But they can either be human and therefore polynomial time bounded, or a superhuman and then an information theoretic, and they can run in unbounded time. We'll talk about that in a minute. The malicious adversary is essentially, we don't say anything about their strategy whatsoever. They can do anything that they want to. Now, there are other possibilities as well. Just one that I'll mention is that of covert, but it won't come up again in the school afterwards. You can think about an adversary that can follow any arbitrary strategy, but is averse to being caught. So if it gets caught cheating, it won't be too happy about that. So if you had a protocol that would guarantee that if the adversary is successfully cheated, then it will be caught with good probability, this may be enough for your application. The good thing about that definition is that it leads to much more efficient protocols. Protocols that are much closer to the complexity of semi-honest than malicious. Again, the adversarial power, this is an orthogonal issue. For each of the definitions, you can talk about a different level of adversarial power. You can have a polynomial time adversary, or you can have a computationally unbounded adversary, and this will give you something which is called information theoretic security. Why would you want that? Why is it even important to think about information theoretic security? Or either you think that factoring may not actually be hard and you still like to have a job as a cryptographer when factoring is broken, and then it's good if you do information theoretic crypto. The other reasons can be, what happens if you're working against possibly very, very, very strong parties? You're running a computation between you and the NSA. You're not necessarily sure that what you think is a reasonable security parameter, what you think is a reasonable length of key is actually going to be long enough. Also, there are remnants left around by computationally secure protocols. So now maybe it's secure, but in 50 years' time, the transcript that you sent may actually be able to be broken open. And then if you had something that's information theoretic, that clearly has advantages of that not being possible. Unfortunately, as we'll see, you can't always do that. But when you can, there are clear advantages. There are also advantages that often these protocols, information theoretic protocols, are actually a lot simpler and a lot more efficient in many cases. Not always and not in all cases, but in some. Another parameter. As I said, we need to have well-defined adversary models, and I'm just showing you that the complexity of just defining who your adversary is quite significant. You have to know what the corruption strategy is. You have to know what they're, are we limiting to something like semi-honest, that can be malicious? What's the running time? We also have to talk about the corruption strategy. Do we assume that the set of corrupted parties is fixed ahead of time? So we have, everyone in this room is running a secure computation protocol, and the question is, are we divided into evil and good people? And that's it, and that would be the static corruption model. So the set of corrupted parties is fixed ahead of time. Or are we all good to start with, or some of us are good to start with, but as time goes on, we get convinced to be bad. And the adversary can corrupt adaptively throughout the computation based on what it sees. Why is this relevant? Why would you want that extra power? Well, there are two good examples. One is the fact that an adversary can, in real life, can often break into a computer online as it's computing. If the protocol takes 5 milliseconds, then maybe you think that's going to be difficult to adaptively, based on what the adversary sees, break into machines. But protocols can run for a long time, and they may even run continuously, and then the ability to break into a machine based on the computation can be significant. Where is one example? Let's say that we wanted to do an election here, we wanted to flip a fair coin in this room. So we could say, well, instead of us all working hard, let's just choose a subset of 5 people or 10 people, and they'll actually run the coin tossing protocol, and we'll save everybody else a lot of work. And as long as one of them is honest, then we have a protocol that's good enough, let's say. So if it's a static adversary, we choose the subset of 10 people at random, then we have a good chance that and the adversary can't corrupt too many people. Let's say it can corrupt a third only, then we have a good chance that this is actually going to be secure. The chances that we chose 10 random people who all fit into the corrupted is very small. But if the adversary is adaptive, then after we chose those 10 people, the adversary can go and choose specifically to corrupt those, and then bias the coin. Now, we're not going to talk about adaptive adversaries too much here, but I just tell you, just want to let you know that it's a nightmare. It's hard. It's hard to prove. It's hard to work with. It's bad news, but it's realistic. What are the execution settings? We talked about the adversary. Now to talk about how the protocol is run. What's the world? What's the setting the protocol is running? So the classic model historically is the standalone model. The standalone model is essentially, you consider a single protocol execution. You can actually look at it slightly different. There's only a single execution that's under attack. Maybe there are many protocols running, but the adversary for some reason is only looking at one protocol. But technically it means pretending there's only one protocol running in the world and nothing else that's connected in any remote way is running. In contrast, you can talk about composition, where we have many protocols running, and there are many different ways of, many different types of composition, but the most general type is what's called concurrent general composition or universal composability. And then we have arbitrary protocols that are executed concurrently, and it's possible that even some protocols are specifically designed to break other protocols. So after you release your protocol, I design another protocol, so that specifically when it's run together with yours, it breaks yours. This is actually a very realistic setting. It's a very important model. But it's in my belief it's not good to jump straight to composition. It's important to first have a good hold and understanding of the standalone model. Why is that? Firstly, it's a good place to start. So computation, as we'll see, is very complicated. And when you actually start reading the full proofs of things which seem intuitively clear on the board on the slides, then you realize that it's even worse than you actually thought. But you're already here, so I can't scare you off. You don't know where to go. Also, the techniques and tools for the standalone model are very, very helpful when you move across to composition. And I would definitely argue that the true goal for our constructions in the end is composition. That would be really what we want. But again, it's significantly more complex, and there are other issues that arise here, like, for example, you can't do it without any setup and other things. So it's not a simple transition. There's more to understand, more to do. But I'm stressing it because it's a very important thing to understand once you have a hold of on the standalone model. So what can we do? This seems like a very, very, I haven't fully defined things yet, but You can talk about very powerful adversaries that can do anything that they want. They can attack the protocol in any way. We want all these very nice properties. Can it even be done? And the good news is yes, otherwise we wouldn't be here. So some of the most basic results are that if you have an honest majority, then essentially any functionality can be securely computed, and this is even information theoretically and with adaptive security. So when you have an honest majority, or 2/3, depends if you need a broadcast channel or you don't need a broadcast channel, you can actually do everything that you want. In the sense of the one-time pad, it's fully secured, you have a mathematical proof that it's secure, you don't need to rely on any assumptions like factoring or anything else, you can do everything you want. Without an honest majority, we have a problem in that we can't achieve fairness. So I gave you a list of things that I want, and one of the things that I wanted was fairness. I wanted a fair world. I wanted that if one party gets output, then everybody is guaranteed to get output. And the unfortunate state of affairs is that the world is not fair and you can't do this. And I'll give you tuition to the proof later on in this session, but you cannot actually achieve fairness in general if you don't have an honest majority. I'm not sure what I meant by that. So, but what can we do? As we'll see in the definition, we'll work out a way to bypass this, and we'll model security without fairness, and then actually you can actually do everything that you want. But here you'll need, you'll do computational security, you'll need to assume a polynomial to an adversary, and you'll also need some hardness assumptions. So with an honest majority, you can do everything cleanly without any hardness assumptions, without any problems. Without an honest majority, you can still do everything, but it's a bit more dirty. You don't have fairness, you don't have guaranteed output delivery either, and you need to assume hardness assumptions, but we're used to that in crypto, so that's fine with us. Okay, now I'm going to start getting into more detail. I'm going to...
When do you decide that you're working with a majority and when not?
Depends on taste, on your assumptions on the world. If, for example, one model of honest majorities, I say that I set up it's you as the user, as the person who's now going to apply secure computation to your problem, has to make a decision. You have to make a decision as to whether or not you can assume that you have an honest majority amongst the parties who are running the protocol. So, is it reasonable to assume that in the university senate meetings they can vote assuming an honest majority? I don't know. In Parliament, I would say no. But if, for example, I'm a service and I'm giving secure computation services, and I'm a big company that I have a lot to lose if something goes wrong, and I have a set of 100 servers, and I say that as long as less than 50 have been broken into, and I spread them across the world, and I have very good infrastructure, firewalls, intrusion detection systems on all of my machines, and they're constantly monitored, and I prove this to my clients, and then I know that they can actually use this service and have their parties send their information to this set of servers, and I'll do the computation for them, which is something that Yuval will talk about on Tuesday afternoon about how you do that. Then it's very, very reasonable in my mind to say that yes, I can assume that at no given time a majority of those servers will be corrupted. But it depends on the setting. Okay, some notations. I'm going to denote the security parameter by n. There are different ways these things are formalized. Sometimes you can formalize security that it holds for all large enough inputs. I prefer to define that it holds for inputs of all lengths and for a large enough security parameter. Just to review what's embedded to a function, it's just a function that's smaller than the inverse of every polynomial. Probability ensemble is just an infinite series of random variables. We have a string A and a security parameter n, and our concept is going to be as follows. We are going to look at A as the inputs of the parties. It will be a vector in our setting, and we don't care about its length, so security will hold for any length of input. And n is going to be the security parameter. We want security to hold as long as we took a large enough security parameter. And we'll be using heavily the notion of computational distinguishability, which basically means that two of these ensembles look the same. Where looking the same depends on what level of security I'm defining. So if I'm defining, when I'm defining computational distinguishability, so the computational setting, that I have two ensembles, X and Y, and basically what I'm saying, for every distinguisher possible, it's polynomial time, and every input A, if I take a large enough security parameter, then that distinguisher will not be able to tell the difference between the two, except for with negative probability. This is basically the type of definition for semantic security, for pseudo-randomness, etc., etc. If I want statistical security or information theoretic security, I can do exactly the same thing, but just let D be unbounded. So the distinguisher can now run any amount of time, and that's one way of defining statistical closeness. And sometimes we can also talk about perfect, where actually the ensembles are exactly the same, and then I just say that these two actually are equal, and there isn't even any negligible difference between them. So this is background that everybody should have seen already. What's a functionality? Now we're getting to notation which is specific to computation. We're looking at, say, m different parties. So there actually a functionality is m different functions, because nobody said that in a secure computation task, every party is supposed to receive the same output. We may be running a computation where I learn one thing and another party learns something else, and it actually may make a lot of sense. For example, two hospitals want to combine their data to do a study, but the first hospital is interested in Alzheimer's, and the second hospital is interested in heart attacks, and but they want to do the study together so they can use computation at once, and one will learn about Alzheimer's and the other one will learn about heart attacks. And for it, you have an input vector of X, which will be made up of X1 through Xm, which are the inputs of all the parties, and Fi of X is simply a function which defines the output of party Pi. And these functions may actually be probabilistic, so and it's not necessarily a deterministic function of the inputs. Coin tossing is the most trivial way of thinking of that, but you can think about sampling algorithms as well, or anything probabilistic that you'd like.
I think it's not more general than having just one function, because you can have m protocols, each given one function.
Not necessary, it's not true, because if I run m protocols, then what I can do is I can change my input from one protocol to the next. So if I, firstly,
Well, you can run it in a black box manner.
so there's a solution to the definition. I can use a solution where there's a single output in order to get a solution for different outputs, that's true. But as a definition, as a notion, I want to solve this problem. And just to naively run one after the other on different protocols won't solve the problem, because you can change the inputs. But there are other solutions. I agree with you, you can, but as a basic definition, you want this. One notation that we'll use throughout the school is this one, that the inputs X and Y are mapped to F1, XY, F2, XY. That's a way of defining what the functionality would be. Okay, so now let's start talking about how to define security for semi-honest adversaries. Semi-honest adversary is a lot easier because I know exactly what's going to happen in a real protocol execution. I know that all the parties are going to do exactly what they're told to do. They're good children, they do what they're supposed to do, they send messages according to the distribution they're supposed to send the messages according to, and this makes life a lot easier. The basic paradigm behind the definition of secure computation is that of simulation. And it's not by chance that secure computation came, or at least the GMW construction came very soon after zero knowledge came out. Also as a tool that's used to help to come up with solutions, but when we started defining things, this was a very, very key tool. So the idea is that of simulation is as follows. Given the input and output of any party or any subset of parties, you're able to actually generate a transcript that looks exactly like or close to a real protocol transcript. So if let's think about two parties for a moment, the question is, did I learn anything more than I'm supposed to? So I have my input, I ran a protocol, and I got my output. Another question is, did I only get the output or did I get something else? Because essentially, I saw much more than the output. I got my output, but I also got this whole transcript of messages going back and forth. So did I learn anything from those messages? Well, if I can generate those messages myself from the input and output, then I obviously didn't learn anything, because I could have done it myself. at least computationally. I may not be able to really generate it exactly, but to something which looks exactly the same or close enough in terms of its computationally distinguishable, I can, then it means I can't do anything that I could have done beforehand. And again, because we're in a semi-honest setting, the inputs are well defined, and this is very, very important. We'll talk about it later. In general, the input of an adversary is not necessarily something that's well defined. In the semi-honest setting, each party has an input. The parties do what they're supposed to do. That means they use those inputs. So the simulator will now just get the party's input and output, and will try and generate the view. The actual definition says as follows: for every adversary A, every semi-honest adversary A, and I explicitly didn't quantify what the running time of the adversary is. I'll explain why in a second. There exists a simulator S, so that for any subset of corrupted parties that there are, and every vector of inputs, so I'm quantifying over all possible subsets over all adversaries, all possible subsets of corrupted parties, and all possible inputs, then I want the following two distributions to be close. By close, I'll define again in a second. The first distribution is the output of the adversary A. The adversary A, we didn't mention what does it mean in a multi-party setting. The adversary A basically controls all of the corrupted parties. So if in this room there are 10 corrupted parties, that means the adversary controls all of those 10. In the semi-honest setting, controlling doesn't mean too much. It means that the adversary gets to see everything that they see. So the 10 people here that are corrupted are all essentially colluding. The adversary can see all of their messages that they sent, that they received, their inputs, their outputs, etc., etc. So we want the output of the adversary, together with the outputs of all the honest parties after protocol execution, to look like the output of this simulator S, given the inputs and outputs of all the corrupted parties, to look the same as that together with all of the outputs. Again, I want the simulator receives the inputs and outputs of the corrupted parties and generates some output. And the output of that simulator together with all of the outputs should look the same as the output of, I guess this should be just the honest party's outputs here actually. We want that to look the same as the output of the real adversary after a real protocol execution, together again with the outputs of the honest parties. Okay, it's a little bit confusing because let me just ignore the second half of the sentence first. The output of the adversary the output of the simulator getting just the inputs and outputs of the corrupted parties should look the same as the output of the real adversary in a real protocol execution. That's pretty simple. That makes sense to everybody. It means that the adversary didn't learn anything. But I'm actually asking for more, and I want to look at the joint distribution of the output of the adversary together with the outputs of the honest parties. This is more complicated, and I think in the next slide I'll explain why. But this is a hint as to why things are actually complicated when we start getting down to details of computation. We need to actually look at this joint distribution. So let's first look at what close means actually. Okay, so actually only later on I get to the joint distribution. So for now, if you feel more comfortable, just think about the fact that the output of the simulator is close to the output of the adversary, and that's it. It means I didn't learn anything, although later on I'll show you that it's more complicated. What's close, this again depends on the setting. It's not just what's close, it's also what's the power of the adversary. If I take a polynomial time adversary and define close to be computational indistinguishability, then I have computational security. If I take an unbounded adversary and I look at statistical closeness, I get statistical security. If I take an unbounded adversary and look at the distribution is identical, I get what's called perfect security. Okay, so let's look at this in pictorially. I have two parties, X and Y. They're running a protocol. The semi-honest, I know they're actually running that protocol. It's supposed to happen. So let's think about this party as being the semi-honest party. So this is the corrupted party. They actually ran the protocol, and they get for output, they get the output they're supposed to, f of X and Y. Let's assume they get the same output here. And they also get a transcript. And this transcript, we're asking, does it reveal any more information than it should? So it doesn't, if it's possible to construct a simulator that gets the input X and f of X, Y, and essentially runs a protocol, is able to run a protocol or generate a protocol transcript together with the corrupted party that looks exactly like they did beforehand. So this semi-honest party still outputs f of xy and a transcript, but this time it's not actually running a real protocol to someone who knows why, it's running essentially with a simulator. This is actually a black box definition, but it's more the intuition that I'm interested in. It's running a protocol with someone who only knows its own input and own output. There's no y appearing here, and that's what's important. If y appeared here, then it would be exactly the same as the previous slide. So obviously we're having a computation here which depends on x and y. And here we're saying the computation no longer depends on x and y. The computation only depends on x and f of x of y. Or essentially I can generate something that looks the same given only the input and output. Okay, so what looks like a joint computation is really something which is less. Let's think about for a second. It's
You still aspire for correctness, full correctness, or maybe the outputs are only close?
so here's okay. In general, the question is what. In general, correctness is guaranteed by the fact that the output distributions that always look the same are. Let's go back to the definition. Here. So in this world, here S is actually given the output of S is put next to the real outputs. What do you mean the real outputs? These aren't computed by a protocol. That's the actual function outputs. And here, the outputs of the honest parties are given after a protocol execution. And these are supposed to look the same. So it means that it must be correct because these are actually correctly computed. That's the actual function output. And here it's the output of a protocol execution. Now, because it's computationally indistinguishable, it means that it's guaranteed up to a negligible factor. In general, I don't care about negligible factors. As far as I'm concerned, they don't exist. The correctness is guaranteed by that. So this is wrong, okay? So it's not true that correctness is not an issue. Correctness is an issue and is guaranteed by what I said. Independence of inputs and fairness are non-issues in the semi-honest model. Why are they non-issues?
Because you have to follow the protocol.
Look, you're following the protocols using your input, your given inputs, so there's no issue of independence of inputs. And you have to follow you're following the entire protocol, so you're not going to stop in the middle. So if everyone's getting output at the end, when they're honest, then everyone's getting output at the end when some of them are semi-honest and corrupted. Why is privacy guaranteed by this definition? Because y is not used by the simulator, and think about the idea that if the adversary could compute anything after the protocol execution, then it could compute that given only its input and output. Because what it would do, it would simulate the protocol execution and then do whatever computation it did. And this is exactly like zero knowledge. Okay, so the same reason that zero knowledge is guaranteed that nothing is learned, the same thing is here. All I have is my input and output, and I'm able to generate the same thing and then do whatever I did. So obviously I'm not doing anything which depends on y that's not derived from f of x of y.
Well, which part of the theory goes the question whether f of xy is something about y? For example, if it's equal to y.
I don't care. I'm in the fortunate position of not caring. There are other people in the world who care about that. The question of what function should be computed is orthogonal, a completely different question to the question of how to compute that function while revealing only the output. So if your computation is interested in the question, give me a function that you want to compute already, that you've decided is okay to compute, and now I'll show you how to compute that without revealing anything but the output. And then you'll say, but is the output okay? I'll say, go to people who do differential privacy. There's a whole other world. They do very nice work. Ask them, I don't know. Right? Secure computation doesn't deal with that question, but it's an important question. For example, if the two of us were to run a protocol computing the average of our salaries, then eventually we'll know each other's salary. If we did it with 100 people, it's a different story. But with 2 people, obviously, it's a nonsensical computation.
If you go back to the picture of the simulator, is its input x the same as the semi-honest?
Yes.
What is it?
Because it's semi-honest, I know what the actual input of that semi-honest party is going to use in the computation. In the malicious world, I don't know. And that's the part of the problem we actually start defining there. But here I know, and therefore I can utilize that and say, okay, so I'm just computing x and f over x, y, and I'll give the simulator that and see if it can compute it. Everything is well defined. Everything is straightforward. As you can see, even straightforward is not so straightforward as computation, but it's not too bad. Okay, any more questions on the definition? And let's get back to the complicated part. I said that we actually need to look at the joint distribution of the outputs of the adversary and the honest parties. And this is confusing, because everything that we said basically until now, apart from the question that I answered from Eran over there, talked about privacy. The adversary can't learn anything more than it should have because it can generate its view given only the input and output. So why do I need to throw in the outputs of the honest parties? So one answer is, I want correctness. I want to guarantee correctness. But that's a bad answer. Why is that a bad answer? Any ideas why it's a bad answer?
So already a given correctness.
It could already be a given. It's not because I didn't define it, but I could very easily say the protocol has to be correct, meaning that if all the parties run correctly, honestly, then the output will be correctly distributed. And I want simulation. I can define it as two separate properties. And this is a much, much easier thing to do. I like complicating people's lives, but not unnecessarily. And to point it as a joint distributions are much, much more difficult to analyze. I need to talk about the outputs of the honest parties together with the output of the adversary as a joint distribution that they'll look the same. Why am I doing that? Why am I complicating your life? So I want to give you an example of what would happen badly if I didn't do that. The best place actually to look for more information about this specific technical detail, which is very important, is in Kennedy's 2000 paper in Journal of Crypto, which gives the basic definition of standalone, and also in Oded Goldreich's Foundation of Cryptography book, the second volume, we also discuss these issues there. So let's look at the following functionality. A outputs a random bit and B outputs nothing. Okay, that's a very, very simple functionality. And obviously, you can ask, well, it's easy to write a protocol, right? What's a protocol that securely computes this? Give me a protocol that can compute this function? I know it's idiotic, so. Don't send anything, A just flips a bit and outputs it. The question is, can I give you a protocol, a different protocol, which will still be secure by the definition if I didn't join the outputs of the adversary and the honest parties, but really should not be secure. So let's look. It's clear that B is not supposed to learn A's output bit. Let's look at the following protocol. Instead of A just choosing a random bit and outputting it, A is going to choose a random bit and send the bit to B, and B will ignore the bit and output nothing. But let's see if it's secure if I only wanted to separately say the protocol is correct and separately say that the protocol preserves privacy. Okay, meaning the output of the adversary is indistinguishable from a real execution and a simulated execution. So let's look at what happens for A. Okay, so the protocol is correct. Clearly, the protocol is clearly correct because A chooses a random bit and outputs it. And the fact that it sends a bit to B doesn't make a difference. B doesn't output anything, so the output is correct. A also doesn't, if A is corrupted, nothing bad happens because B is now completely honest, so nothing's wrong. What happens when B is semi-honest and B is corrupted? Now, I'm going to give you a simulator. The simulator does the following thing. It outputs a random bit. It gives B a random bit. And that's it. Now, the distribution, let's look at the adversary's view. In a real protocol execution, what does the adversary see? What does the corrupted B see? In a real protocol execution, what does the corrupted B see? A random bit from A. And the simulation, what does the corrupted B see? A random bit from A. It's exactly the same. In fact, this is a perfectly secure protocol. So the definition where I separate, I know I'm complicating life, but life is complicated. Nothing I can do about it. So if I separate correctness from the view of the adversary into two separate notions, then this protocol is perfectly secure. And this protocol should not be secure. Okay? This is generally the problem of defining things that are supposed to model something in the real world, but we have to understand whether what we're actually getting is really enough or not. So that's why it took many, many years to come up with the correct definitions. The task of defining computation properly took a decade. It starts in the early 90s, 91 I think, or no, even the late 80s, 89, and finished essentially in 2000. That's the time you could say that it was solidified. And exactly these sort of subtleties are what comes up. See, if I separate correctness and separate the output of the adversary simulator, then this protocol is secure. But if I look at them as a joint distribution, is it secure? Why not? Why not? Why isn't it secure if I look at it as a joint? In the real protocol execution, the corrupted B saw the same bit that A outputs. But in the simulated version, the bit that B sees is independent of A's output. So this cannot look the same. Okay, in particular, just think about B that outputs the bit that it sees. Then in the real adversary, in the real protocol execution, they will always equal each other. Always. But no simulator in the world can make B output the same bit as the honest A because it doesn't learn anything about the bit that A outputs. It doesn't get any output, so it can't know what A outputs. So this protocol is not secure in that sense. Now, I've complicated your life.
It will look the same.
One, half the time. Half the time is not enough. Has to be all the time except for a negligible fraction. Fortunately, this is the good news. After giving you the bad news, I give you the good news. If the functionality that I'm computing is deterministic, then it is enough to separate those two things out. And fortunately, most of the time we're computing deterministic functionalities, and then we save this headache, because the joint distributions are difficult. So in the case of deterministic functionalities, it suffices to separately prove correctness, meaning that I show you that if all the parties are honest and they run the protocol correctly, then all of their outputs are the same, compute the correct function except with negative probability, and separately generate the output of the adversary or the view of the adversary using simulation. So when the function is deterministic, this is good enough, because if you think about it, when the function is deterministic, the output depends only on the inputs. So it's fully determined already. Whereas this counter example that we had is exactly where the output is not fully determined by the inputs. Okay? So I made life complicated for you all, and now I'm saying most of the time you can forget it, but don't completely forget this issue, because this is one of the big mistakes that people make when they actually start working on C computation, is to forget about this and to prove it separately when actually you can't, or to forget to prove the joint distribution. And it's easy to forget to do that because it's something that you want to forget. Okay, let's move on. We're now finished with semi-honest adversaries. We're happy with that. We can do that. No problem. Let's go on to malicious adversaries. And just to show why this is more complicated, let's make a first attempt. The first attempt is the same thing. I want to require a simulator, the existence of a simulator that generates the adversary's view given the inputs and outputs of the corrupted parties. Now, what's wrong with that as a basic notion or as a starting point for a definition?
You don't have much guarantees on the inputs.
You don't know what the inputs are. In particular, what about if, let's think about an adversary that sends, I don't know what message, it sends random garbage.
Nothing.
Or sends nothing, seems, or maybe, okay, even sends nothing. Well, it depends what the protocol will answer, but we don't know, to some extent, anything you do sort of implicitly defines some sort of input, maybe, right? But we don't know what that input is. That input is not well defined. The fact that the adversary, a corrupted party, has a certain string written on its input tape doesn't mean that's the one it uses. The adversary could just choose a completely different input, or it could implicitly define its input as the computation carries on. For example, by seeing what the other parties do, and then choosing its input based on the messages that it saw from the other parties. And that means that I can't tell the simulator, here's the input-output, now run, because the output depends on the input. But the input depends on the protocol execution. So a simulator can't first be given the input and output and then work. Does everyone see that? If the input can depend on the protocol execution and the output depends on the input, then the simulator can't be given the input, output and start working, because then it won't end up ever looking like what happened in the real world, because in the real world, the input of the adversary depends on the actual execution, but here it's done in reverse order. The simulator first gets the input, output and then generates the protocol execution. So it doesn't work. This is what we said now. It's not that the adversary doesn't necessarily use the input on the input tape. It doesn't. The inputs aren't necessarily even explicit, so we can't really relate to them. On top of that, we talk about a whole list of properties that we need, like independence of inputs. Correctness actually is covered by the one, fairness, guaranteed output delivery, and they're not covered at all by looking at the view of the simulator. The fact that I have a simulator that can generate the view of a corrupted party doesn't mean that there's independence of inputs. Doesn't mean that there's fairness. Sorry? Any question? It doesn't mean that there's fairness. It doesn't mean that the adversary can't get output while the other party gets output. It's not connected at all. This issue of correctness and privacy, it's interesting just to talk for one moment. Can we actually separate out these different properties at all? Are correctness and privacy different issues? They look to be something completely different. Privacy is, can I learn more than I should? And correctness is, am I computing the correct function? But what happens if I break correctness by, instead of computing the correct function, which I don't know what it outputs, I make the protocol compute a function that reveals the first input bit of the other party? Did I break correctness or did I break privacy?
Yes.
Both. It's an attack on correctness, but the attack on correctness actually breaks privacy. So you can't separate these things out. What about independence of inputs and privacy? Can you separate them?
No, because if one input depends on the other, then you already learned something at the end.
Right, the fact that if I can make my input depend on the other party's input, then I can use that in order to learn more than I should. For example, let's say we want to compute secure equality. So I have a string and someone else has a string. We want to know if we hold the same string. If we hold the same string, then we output that string, because we know it already anyway, so why not have that be as part of the output? If we don't hold the same string, then we just we get 0 as output. In general, I don't know how to make my input always equal the other party's input. Maybe it's a random string. But if there's no independence of inputs in the protocol, then I can maybe always make my input equal the other party's input and then learn completely that input. So again, you can't separate out either independence of inputs and privacy. These things are all completely intertwined, and so we need a definition that's actually going to deal with everything in one shot. Privacy, correctness, independence of inputs, fairness, all in one shot, give us everything at once without separating anything out. Not even for the case of deterministic functionalities. Here in the malicious setting, you can't separate anything out in general, at least. Maybe for specific tasks you can, but not in general. Okay, so in order to come with a definition, let's think of what's the best we could hope for? What would be the best thing in the world? The best thing in the world is actually if there are people that we could trust. Right? If we had people in the world that we could trust, then we wouldn't have any problems. So let's assume that there's just one person in the world that we can all trust. From Europe, from the USA, from Israel, from Iran, from Egypt today, from Russia. Let's just, there's one person that we can all, the entire world, trust. This is a really ideal world. And what would happen is that all parties would send their inputs to that trusted party. That trusted party, I'll set it encrypted on a secure line. That trusted party will say, don't worry, I'll do the computation, I won't tell anyone anything about the output. The trusted party will compute the output after getting the inputs from everybody, send each party its designated output, again on secure channels, encrypted and everything, and everyone's happy. Did you learn anything more than the output? What did each party learn?
The output.
The output. What about correctness? Is the output correctly computed? Yeah, because the trusted party, who's incorruptible, computed the function correctly. What are independence of inputs? Are they guaranteed? Why are they guaranteed? Because everyone sent their input, and then only afterwards, like after everybody's input was received by the trusted party, it was computed and the output was sent. The only thing that you did was send your input and get back an output. So obviously it's independence of inputs. What about fairness? Same thing. The trusted party is fair. Once it gets everybody's inputs, it computes the function and sends the output to everybody at the same time. So this is a great world, and this is what I'd really like the world to look like. The real world doesn't really look like that. Just note one thing, the only thing the adversary can do in such an ideal world is actually even just to choose its input. It can't do any attack, there's nothing it can do but choose its input. So, in cryptography we can actually make the real world look like the ideal world. We can't do it in work, but that's going to be what we want to do. We want to say that a real protocol will be secure if it looks like an ideal execution. Now this is obviously the best that anybody can hope for. We already said that in one foul swoop we got all of the properties at once. The guarantees are really easy to understand, right? Anybody can understand that if this is what the protocol essentially guarantees, we can explain that even to our grandmother, right? It just looks like there's a trusted party that everybody trusts and we just send it to them back. Even the astronomers could understand. Now, how do I formalize this notion? I say the following thing. I now have an ideal world and have a real world. My ideal world I define. This is the ideal world, right? This is actually a definition. I can formally define a setting where I have parties, I have a corrupted party, I have an adversary who corrupts a subset of the party and tells them what input to send and gets back their outputs. The honest parties just send their input and get back output. This is a real computational setting. Instead of M parties, there are M+1 parties. That's all. There's an additional trusted party. And we also say that the adversary can corrupt a subset of the M parties but cannot corrupt the trusted party. So that's a computational setting. And what I say is that for every adversary A that attacks a real protocol execution between the parties, there exists an adversary S for the ideal model. And this S is also simulated because it manages to simulate a real protocol execution while actually running an ideal world execution. And for every A, there exists such an S that runs in the ideal model, such that again, the output distributions of all the parties, the honest parties and the adversary here we have no way of separating it out, so that's life, are close. What does close mean? As beforehand, if the adversaries are polynomial time and we take computational distinguishability, it's computational security. If the adversaries are unbounded and we look at statistical closeness and statistical security and identical distributions, then we look at perfect security. Okay, so that's the definition of security for malicious adversaries. And we call S a simulator because it manages to simulate a real protocol execution while interacting in the ideal world. Can anybody think what's the fundamental difference between the semi-honest simulator that I wrote and this simulator? There's a fundamental difference between the type of machine that it is. The semi-honest simulator receives input. What's its input? The input-output of the adversary, and generates output. What's the output? The view of the adversary, the view of the protocol execution, the adversary's output, it's the same thing. It's a non-interactive machine, it's an algorithm. The simulator is an algorithm. It just gets input and generates output. What about this simulator? This is a protocol or an interactive machine, exactly. This machine is actually running a protocol with an external party. It's going to send inputs to a trusted party, get back outputs, and while it does that, it's going to generate interactively a view of the adversary in a real protocol execution. So we don't have this problem of, well, if the input of the adversary depends on the transcript, then how can we have the simulator get the input and run? So now the simulator doesn't get the input and run. In fact, when you do security proofs in this model, then what you actually essentially do is the simulator will start running the adversary, send it garbage value or something, somehow learn the implicit inputs that the adversary is using, send them off to the trusted party, get back the output, continue the execution and make it look to the adversary as if this is the output that it's supposed to get. And here, as I said before, we always look at the joint output distribution. Here you can't separate it at all. There's one work that I know of that tries to give a general definition of secure computation that separates out some of the things. It's in order to attempt to solve problems of composition, and it turned out to be very, very complicated. So in general, you can't separate these things out, and it's not worth trying unless you're trying to do something that's impossible under these definitions. Let's look at this graphically. Here we have a real-world protocol, and here's our ideal world. In the real world, the parties actually run some sort of protocol execution, and they output something. And here I didn't write here f of x, y. I didn't write f of x, y because there's no guarantee this x is what was used. Instead, there's some sort of output. The output here, though, is not arbitrary because it's the output that's designated by the protocol. The protocol told this party, based on your input and what you saw here, this is what you should output. Here, the adversary can output whatever it wants. In the ideal world, the parties send, well, this party, the honest party, sends y, and this party sends not x, but just some x prime. But then both of them are guaranteed to get f of x prime y. So the inputs are sent. Once the inputs are sent, they're now fixed, and they're sent independently of each other. And then both parties are given the correct outputs, f of x prime y. Again, using the same f here, but in general, it doesn't have to be the same. And what's the requirement? That these should look close. In other words, this arbitrary output here should look like this arbitrary output. And this output here should look like this output. Now, if I run this twice, if I run this simulator here twice, I run this executing the ideal world twice, is it going to be the same x prime each time?
Not necessarily.
Why not necessarily?
Depends on the...
And the adversary may be, it may be probabilistic, but in the adversary it's not. It may choose the inputs based on what it sees in the execution. So in the real world, it could maybe receive the first message from here and then apply a pseudo-random function to that message, get some string, and then use that to sample an input. So when you run these things many times, you're actually going to get different values coming out here. What's important though is that the distribution of the values will be essentially the same here and here, or essentially the same, again, depends on the level of security you're looking for. So what's the formal security definition? That's if you just like to read a lot, but that's just in the slides we have in the slides. Again, for every adversary A, there exists an adversary S with the full quantifications of what I want the adversary to be, non-uniform, polynomial type, non-uniform because we're quantifying overall x's. All auxiliary inputs, that we need that as well. The joint outputs of the adversary and the honest parties in the real world are indistinguishable from the joint outputs in the ideal world. This is obviously the definition only for the computational setting, because I'm requiring polynomial time parties and I'm requiring indistinguishability. And this is wrong, because it needs to say probabilistic. A, by the way, I can get away with having, I can let A be deterministic because it's non-uniform, but I can't let S. S has to be probabilistic. Again, that's the different levels of security. So what are the properties that I get from this definition? The privacy follows from the adversary's output. The adversary's output in the real and ideal world looks the same. In the ideal world, the adversary only receives the output and nothing else. Therefore, in the real world, the adversary couldn't learn anything more about the input of the other party. Because if the adversary after a real protocol could learn more, then there's no way that any simulator could make things look indistinguishable. Okay, that's the main point. It's similar to the coin flip that we talked about beforehand. If in a real protocol execution I could learn more, then there's no way that an adversary could make, that a simulator could make the two distributions look the same. Correctness follows from a completely different reason. The honest party's output. Does anyone want to explain that to me? What does that mean?
The honest parties follows the protocol.
Yeah.
So they will output correct results.
But the adversary is malicious and it might Or that the adversary is malicious, maybe it makes the protocol, maybe it makes them output something which is incorrect.
But they cannot in the ideal model.
Exactly. In the ideal model, the honest parties will always output the correct value, a correctly computed value based on the inputs that the simulator sends to the trusted party and the inputs of all the honest parties. That means that in the real world, the same thing has to happen. If something else happened in the real world, then again, the distributions would not look the same, even by just looking at the subset of the honest parties inputs. Okay, so the correctness follows, privacy follows from the adversary's output, and correctness follows from the honest party's output. Independence of inputs, again, follows from the ideal execution. We can know by looking at the distribution of the outputs of the parties that in the ideal execution, we know that all the inputs were independent, therefore it has to be also in the real world. And if we think back to the examples that we gave beforehand, if it's possible for me to always win the auction by $1 in the real world, in the ideal world that won't be possible. In the ideal world I have to give my bids without knowing anything about the other party's values. And if there is any randomness in the other party's values, I won't be able to do that, if there's any uncertainty. Again, fairness and guaranteed output delivery are all guaranteed in the ideal execution. Yes?
How can you say that, before you told us that these things are intertwined, so you cannot really say that one thing follows from one thing. They all follow from the ideal world model. And
Yes,
the
yes.
indistinguishability.
They all follow from the ideal model and the fact that it's all together, but you can look at specific properties and say, how is it guaranteed? You're right, this is actually technically not the best thing to do. It's a nice slide for intuition, but you're right, technically it's best just to say, the ideal model looks like that, and everything is indistinguishable, so that's all I need. You're right. Unfortunately, the ideal world is sometimes too ideal. Or meaning that we can't necessarily always actually even meet this definition. And one problem is that of fairness. So if you want to get intuition as to why fairness is impossible in general, I'll give you an incorrect intuition into it. In other words, it doesn't really transfer across, but there's something to it. Think about a protocol which guarantees fairness. That means that if one party stops early, the other party still outputs the correct output. Let's think now about, so it's an R-round protocol, and let's think of what happens if in each round both parties send a message. In the last round, one of the parties doesn't send its message. Okay? We now have a truncated protocol. I removed the last message. Do both parties get output? Why do both parties get output?
Because it's fair.
The party that sent the message, the party that didn't send the message in the last round, received its last message, got a full transcript, so it obviously gets output. And the other party, because of fairness, right, the protocol is supposed to guarantee that if one got output, the other got output, so the first party got output. The second party also has to get output. Now I have a protocol where both parties get output, but it has one message less. Let's do it again. Let's remove the last message. And then I get an empty protocol, and we know that that's not possible. Now the intuition is incorrect, because actually once I start peeling things off, who says the correctness is still guaranteed, for example. But it works for coin tossing. Now, in general, fairness is a problem. We know that in general it can't be done, and the belief until a few years ago was that nothing could be done fairly, and then a recent paper showed that you can actually do some things fairly. So we don't really know exactly what can and cannot be done. We know that in general you can't do it. We know that if you do want fairness, it's going to take a lot of rounds, and we know that it's going to be very, very ugly. So without an honest, this is all without an honest majority. So without an honest majority, what we actually want to do is just get rid of fairness as a requirement. Because we can't always achieve it, and when we can, it's very, very difficult. And you may say, why is that reasonable? Maybe I need fairness. There are two answers I have for that. Firstly, maybe in some settings you don't need fairness. And secondly, you can't always get what you want. You can try, but you just got what you need. So we're going to change the instructions of the trusted party in order to basically bypass the whole fairness issue. So I'm going to change the ideal model. The trusted party receives the input from all the parties. It's exactly the same. Now, beforehand, the trusted party just computed the output and sent the output to everybody. Now the trusted party is going to compute the output and send the output only to the corrupted parties. Notice that the trusted party first received the input from everybody. So independence of inputs, etc. is all still preserved. But instead of sending the output straight away to everybody, it's going to send the output only to the adversary, only to the corrupted parties. In the ideal world, I know. In the ideal world, the corrupted parties are wearing red. In the real world, there are a couple people wearing here red, I don't know. Shy, somewhat malicious, but... in the ideal world, it's a mental experiment. I can say whatever I want. The point is, in the real world, I don't know who the corrupted parties are, and the protocol definitely can't refer to them in any way. If I knew who they were, you're right, I wouldn't have any task at hand. The ideal model is just for the purpose of a definition. The trusted party sends the output to the corrupted parties, and the adversary says something simple: continue or halt. You know, it's, okay, give the honest parties their output as well, or no, make them output some special abort message. If the trusted party gets back continue from the adversary, then it sends the outputs to all the honest parties, and otherwise it sends a special abort message. And now all I need to do is just take my definition from beforehand, which says that for every real adversary A, there exists an ideal adversary S, but now I just use a different ideal model. And the ideal model that I'm going to compare to is this ideal model. And this definitely doesn't guarantee fairness, but it's clear that everything else that I talked about is guaranteed. I haven't harmed correctness or independence of inputs or privacy or anything else, because the only question is, did all the honest parties get their output or not? And that depends on whether the adversary decides to say continue or halt.
I'm confused between adversary, honest party, and corrupted parties. What's the adversary?
The adversary controls a set of corrupted parties. Take your honest parties, divide them up into two subsets, one of corrupted and one of honest. The adversary is controlling all of the corrupted parties together. It doesn't have to, in principle, be defined that way, and I think actually there's a good reason why we should try and define things where not all the corrupted parties collude, but I don't know how to do it. And I tried, but you guys should try also and hopefully succeed. There's good reasons why you might want to do that. I can talk about in a break if anyone's interested. Yeah?
So does this apply to the adaptive model?
This is orthogonal. For any adversary, I can be polynomial time or unbounded. I can be, well, I'm talking malicious here. I can be adaptive or static. Oh, sorry, you're right. In the ideal model, I have to allow the adversary also to send out corrupt messages. Say, I want to corrupt this party, and then get back the input and output of that party as well. In the ideal model, it's actually there are more. I take it back. This is the static definition. For adaptive corruptions, there are more complex issues. Also, you have to issue corrupt messages, and you also need something called a post-execution corruption phase. It's more complicated. So this is the static one. More questions? Another thing that we can talk about is not just functionalities that are input-output, as in non-interactive functions. We can talk about functionalities that are computing stages. So you get inputs and provide outputs in stages. Some classic example is mental poker. So in poker, we first deal the cards. Everybody gets to see their cards. They got output. Right? I received cards. I don't have output. And everybody chooses which cards to throw, and they get back additional cards. That's another stage. And this keeps, and we can keep doing this in a number of stages. Another is a commitment scheme. In the commitment scheme, first I commit to my input, and then later on I reveal it. So it's a two-stage computation. So not all functionalities that we're interested in is a function which has input and output. Sometimes I want things that are reactive and have a number of stages. And this is also useful if you want to provide other relaxations to the ideal model. For example, I could have defined the relaxation to the ideal model in the previous slide, not by changing the trusted party, but by changing the functionality. The functionality would get the inputs from everybody, and now provide outputs to corrupted parties, get back another input from the corrupted party, from any corrupted party, say continue or halt, and then provide outputs or not to the honest parties. This can be very useful. These relaxations can be very useful when you want efficient protocols. For example, let's say I have a protocol which does a fantastic computation, but it leaks a little bit of information. And in my opinion, the information that leaks is not significant. For example, I managed to have some protocol that computes some statistical measurements over a massive database, but it reveals the parity of the other party's database. And I think it doesn't matter, it's not important. Then I can model that protocol to be secure by changing the functionality. And so you're not only going to get the statistical measurements, you're also going to get the parity of the other party's database as part of the legitimate output. It might sound like cheating, but it's not cheating at all, because when I now come to the user, to the hospital, and say, here is something for computing statistical hypotheses, statistical tests on the databases without revealing anything, except that you should know that what will be revealed is the parity of a database, they can decide whether that is legitimate or not legitimate for them. Everything is very, very clear and explicit. There's no like, yeah, this is basically secure, but we have something else, and everything is very explicit, very formal, very rigorous, so this is a very good way of working. And the definition that we saw extends very naturally to this, so there's no problem, and it's a very, very useful type of tool. In fact, there are some protocols that are intuitively are secure, but without defining the functionality in a reactive way, we don't know how to prove that. Okay, so what's the advantage of this approach? We mentioned it beforehand. It captures all applications. It's very, very general. The specifics of the application are only relevant in defining the functionality. Right? I have a general definition. Now when I want to look specifically at some application, the change that I have to make is simply to define the functionality appropriately to what I'm computing. And also the security current guarantees are very, very easily understood. All I need to do is look at the ideal model. So this is something that Boaz asked beforehand. In general, we talked about probabilistic functionalities, reactive general functionalities. Each party can get different output. When we construct protocols, especially general protocols that want to prove feasibility, can we actually compute, can we actually meet this very, very stringent definition, it's easier to work with more limited types of functionalities and have small lemmas which will say that it's okay if you prove that, then you can also do the general case. So what are some things? It's enough to show that you can generally compute deterministic functionalities, because if I'm given a probabilistic functionality f, then I can define a deterministic functionality g to be g of x r y s would be f of x y with randomness r x or s. So each party provides randomness as their input, and you XOR it and use that as a randomness to compute f. And this is now a deterministic functionality. Now, in order to prove that this suffices, I need to use the more general definition of probabilistic functionalities. Once I've proven this once, I can now just work with deterministic G, and then I have if I'm in semi-honest setting, then I can now work separately with correctness in the adversary's view. Also, single output functionalities, instead of having a different output for every party, I can now have one output, the same output for all parties. Why is that okay? Because what I can do is I can encrypt everybody's output and give each party will input a key, and everybody will get back a vector of all of the outputs encrypted under each party's key. So now there's a single output, but only I can understand my output. Now you want to also make sure that nobody can change things, so you can map things as well. Non-reactive functionalities. So this also means that only it's enough in fact for one party even to get output. One party will get the string of everyone's encrypted values, and then you can just send each party its output. If things are mapped, and they can't change anything anymore. Non-reactive functionalities are easier also. I just have input and output. I don't have multi-stages. So you can do this by having the output of the function be the output of that stage, plus a sharing of the internal state of the functionality. A reactive functionality basically means that I did a computation. I now have some internal state that I keep for the next stage. Because if the stages are independent, then it's not really relevant. But in general, in the poker example, we have the current state of which cards were dealt. In the commitment value before the reveal depends on the commit. So that's what we're interested in. So you just need to spread that state, share it between all the parties, and add a max so nobody can change anything. Okay, we have a couple of things that are very important for us to finish in the next 7 minutes. Yeah.
So before you say that you encrypt the output to different with the power key of
Each part.
Each part, right?
Yeah.
But do you use the same randomness for each of all those?
No.
For the encryption, it's not.
No, you can. Are you saying this is now a probabilistic functionality? There's no problem because I can simply have the randomness be long enough here, so I can use a different portion for each party. One very, very important tool that we need when we want to work with secure computation and prove protocol secure is something called sequential modular computation. And this is an important security goal within itself. To have sequential security and sequential composition, but it's also a very, very important technical tool for proving security. So the idea is that we're looking at the sequential execution of many protocols. So the protocols are run one after the other. It's strictly sequential, meaning that a new protocol only starts after a previous protocol finished. They're also going to allow arbitrary messages between the protocols. So maybe have a protocol, then some arbitrary junk is sent, have another protocol, some arbitrary junk is sent, another protocol, and so on and so forth. Why consider this? Again, this is an important security goal. I don't have general concurrent composition, but I do have something that says that if everybody in the world is writing sequentially, then things should be okay. That's not so convincing, but it's more importantly, it's helpful, it's not crucial for analyzing the security of protocols, not polynomials, protocols. Polynomials, either secure or insecure, but protocols can be, so that's a typo. Let's think about it. I have a protocol which starts off with some abilities transfer, and afterwards a commitment, and after zero knowledge proof, and afterwards something else. Then one thing I can do is do a reduction in my security proof to every single sub-protocol, and that will be difficult. This is going to be a tool which will make life much easier. And in order to see what we're going to get, we're going to define something called a hybrid model. Until now, we saw a real world and an ideal world. And now we're going to look at a mix of the world. In a hybrid model, the parties can also will run a regular protocol. They can send regular messages to each other. But they can also run ideal protocols, meaning they can also use a trusted party to compute some sub-functionalities. Okay, so the trusted party that's willing to that does a few things. It will do a commitment for you. It will do functions F1, F2, F3 for you, and then you want to use that to try and compute something else. So in general, we have sub-protocols rho I, and each rho I securely computes some functionality Fi. And the definition says as follows, that pi, a protocol pi, a big protocol that uses all of these Fi's, securely computes some function G in the hybrid model. So that's a definition of security. Security is basically the same as before. One second. Yeah, okay, so it's not a definition at all. What I'll actually want to do is I'm going to prove that this protocol pi will be secure, not in a fully real model, but where I have some trusted help. So I write a proof of security, but proof of security is much easier because my sub-protocols are all ideal now. Right? If I'm using oblivious transfer or something else, then instead of having a real protocol there, I can actually use a trusted party to help. And then, if once I've proven this, and this is much, much easier to analyze because all of these subcalls are just sending messages to trusted party, getting messages back, then the theorem says that if I've proven my protocol secure in this setting, and each rho I is indeed securely computes each Fi, then when I use a real protocol, that instead of using the calls to Fi, I actually use the real protocols rho I, then everything will be fine.
This is just random inequality.
No. It's not because it's a computational world.
I don't know, as an outsider, it looks trivial.
It's not true once you have to write a reduction.
What?
As soon as you have to write a reduction, that if you can break the protocol pi, then you can break each protocol rho I, then it's non-trivial. More than that, it's not trivial if you didn't define things exactly right. So for example, if you don't have auxiliary input in the definition, it's not going to be true anymore. And there are definitions of computation for which this doesn't hold. The definition I showed you today does hold. But it's non-trivial in that sense. Once everything is set up correctly, then the proof is not different. But it's definitely not trivial. Again, the idea is that if I have sub-protocols that are proven, secure, I can now use those in an ideal way within a bigger protocol and prove the security of a bigger protocol while only referring to the ideal calls to these sub-protocols. And after that, I can actually run the real protocols.
So what happens to your security parameter? Does it blow up?
So this depends on the tightness of your reduction. In general, the composition theorem. I think it's pretty tight, but I don't.
I think it's linear in the number of things you concatenate. Basically, it's like the sum. Because of traffic.
It's linear in the number of calls. You have to go hybrid over the number of calls. So if you have many calls, then you get that sort of degradation. We don't have time for that, so I'm going to skip all of this. There's more slides here than anyway I thought I'd manage to do, but you have them in the booklet there. I'll just give you a few pointers of what I was going to talk about if there was time. There's how to define privacy only, which is an interesting task in itself. Depending on how we're talking about that more tomorrow. And the relationship between semi-honest and malicious security. You would like to think, after everything we've seen, that any protocol that's secure for the malicious setting is also secure for the semi-honest setting, but unfortunately, it's complicated, but I'm not going to go into it. Just to sum up, semi-honest, defining semi-honest, we have the simulator that gets input-output and generates the view. There's issues of the joint distribution or not the joint distribution, depending on probabilistic and deterministic functionalities. In the malicious setting, there's the idea of real simulation, the idea of real paradigm it's called. A very important thing that we only went over very shortly, but it's important to understand whenever you want to prove something secure, is this notion of sequential composition. There's an outline, an idea of the proof also in the slide there, so you can look at later on. And there are advanced topics that we didn't get to, but that's for future issues. So we'll take now a coffee break and we'll come back at 11 for continuation.